recorder started. All right. All right, so I'm gonna get started because I'm not gonna wait any longer. The recorder has started, so you can all, kind of rewatch if you want to. As usual, I mean, that part has not changed. I am going to start up the. Yeah, the other student has not joined us, even though he's supposed to. But I'm going to open up a chat so I can see if there are any questions from him. All right, so what we're going to do today is to talk about local variables on top of all the other things that we have talked about so far. So let's go ahead and take a look at some sample programs. So I'm going to write a program that involves a local variable, and then we'll go ahead and translate it into assembly code. And in the process of translating, we'll go back and review some of the concepts that we should know already. And also at the same time, we will explain the new concept, which is the focus of today's class, which are the local variables. So I'm going to look at the C code and also look at the assembly code at the same time. And I'm going to look at string length, but it's going to be a different string length program compared to the one that I talked about yesterday with my Tuesday class. Sometimes, if you have the time, I know this may not happen at all, but if you do have the time, the sample programs that I use on my Tuesday, Thursday class and the Monday, Wednesday class can be different. So you can kind of check in with the other class, just kind of quickly scan through the whole thing, and if you look at the program, it's like, oh, that's not the same program that we talked about. Then you can decide whether to watch that one also, because the more exposure, I think it's going to be a little bit better. All right. So we are going to go take a look at string length, and this time I will use a more traditional way to do it. This is the recursive way of doing string length, um, which is not a very good way to do it, from the perspective of efficiency, but it is an interesting way of doing it from the perspective of how we can break down a problem into a small chunk of thing to do, plus the invocation of the same subroutine to take care of a smaller problem, but of the same nature. So that's kind of the principle of recursion is like that. So instead of doing this, we'll do it in a much more traditional way. So I will make this program actually compilable. So for those of you who want to actually run this program, you can do so. Yep.
Can we take a look at that other one later, maybe?
Yeah.
Just to take a look at it.
Yeah, sure. Yeah, we can do that, but it's also in the recording of Tuesday, yesterday.
Oh, okay. Okay.
So if I do not have time today to talk about it, you can always just do that too.
Okay.
All right, so there are quite a few ways to do string length without recursion. It depends on whether you want to actually do the counting using a local variable, or whether you want to use a local variable to remember the pointers, and then we can just look at the subtraction between two pointers. So which way do you want to do it? Do you want to do the counting, or do you want to kind of use the subtraction of pointers to do the same calculation?
Subtraction of pointers.
Subtraction of the pointers? Okay, we can do it that way.
I'm just asking what method is that?
Let me do it now, and then and then you can see it.
Okay.
All right.
So string length just how long the string is?
Yeah.
Okay.
How many characters, excluding the null terminator, is in the string? Yep. So we have const char, and we have another pointer here. So we'll say, okay, say beginning. Okay. So the way we can do this, one way is to say beginning is the same as PTR, which is my parameter. And then from here on, we just have to use a while loop here. And if you want it to be a really obscure way to do this, well, let's not do the obscure way. So this is the not so obscure way to do this loop here. If PTR is not pointing to a null terminator, just increment it, and then we look at the next character. So what we return in the end is going to be PTR minus beginning. That is what I mean when I said subtraction between two pointers, because beginning was captured early on. So basically, before I perform the loop, I say, okay, let's make a copy of PTR as my local variable beginning, and then I do the loop. All the loop is trying to do is to find where is the null terminator. As soon as it finds the null terminator, it stops. And then once it stops, then we have the pointer pointing to the null terminator. We have beginning pointing to the very beginning of the entire string. So when you perform the pointer subtraction, then you have the number of elements between those two pointers, which is, in this case, the length of the array. Or I should say the array of the string. Is that okay? Does that kind of make sense?
Yeah.
Okay. So to run this code, okay, we can use main over here. And since we are going to talk about local variables, so now I can say, I'm going to use a local variable, which is an unsigned 8-bit integer to store, I'm just going to call this length here. And length is going to be string length of, say, tag, like this. So that should be 3, and then return 0. And that's the end of the sample program for today. So do we have any questions about the sample program itself? So we all good with the sample program? All right. So now we have to look into the translation of this code. And the main point here is, how do we deal with local variables? So what we want to do is, what I want to do is to go to the notes here, and I want to share with you that I kind of split the caller-callee agreement. So the caller-callee agreement is now kind of shorter because it only deals with the actual agreement between the caller and the callee. And the extra stuff that only applies to the callee is now in a different module. And that other different module is called callee only considerations. And this is where you can find kind of like a table. And I think this is going to help you guys understand how things are organized on the stack. So in this table, going up goes to higher memory locations. Going down means that we go into lower memory locations. So whenever you call a subroutine, there are a few things that has to live on the stack. So the first two items, or the first chunk of items here, would be the arguments that the caller is pushing on the stack. So the way arguments are arranged is the last argument has the highest memory address. The first argument, if any, has the lowest memory address. Okay, and both of these must, not both of these, all of these, okay, because you can have any number of arguments. All of these need to be pushed by the caller. The last thing that the caller needs to push is the return address. The arguments are optional. Okay, we have had functions that do not have any arguments, but today we're going to have to deal with arguments. And the return address is not optional; it is mandatory. So that would be the last item that the caller needs to push before continuing to execute in the subroutine. This part here, all the way up to the return address, that is stuff that we have talked about so far in this class, is to take care of the arguments, take care of the return address. Do we have any questions about those particular items? Okay, no questions. So now we're going to move into things that are specific to today's lecture, and those would be local variables. So you put your local variables on the stack below the return address. Now, there are several reasons why that has to be the case. One is by the time the subroutine is called, the stack pointer is pointing to the return address. So, you don't really have a whole lot of options of where else you can put your your local variables. So the local variables has to be declared, or they have to be allocated below the return address. And that has to be done by the callee, because the caller doesn't know. The caller doesn't know how many bytes are needed for local variables. Only the subroutine being called would know how much space is needed for its own local variables. Does that make sense? So this entire thing is not constructed all by the caller or constructed all by the callee. The first bunch of items, these are constructed by the caller. And then the last few items, which is from here all the way here, these are constructed by the callee, the subroutine being called. Is that okay? So when I said, these are allocated by the callee, what do I mean exactly by quote unquote allocated? That means the stack pointer needs to be adjusted to point here. Is that okay? And that's the job of the callee to move the stack pointer at the entry point. It's going to be pointing to the return address. And then when it is done allocating for the local variables, the stack pointer will have to point to the lowest local variable that applies to the subroutine. Do we have any questions about the concept? We are not talking about how it is implemented. We are only talking about the concept at this point. Where do we put the local variables? This is all good? Okay. So based on this picture, I have a suggested way to organize and use symbols so that we can actually more easily keep track of things. Oh, that is not working. Okay, where's my mouse pointer? There we go. There we go. So the way I would organize all of this stuff here is to use labels. So this label here is the first local variable. It has an offset of 0 from where the stack pointer should be pointing to after the local variables are allocated. Okay? Because that would be the last thing that I allocate on the stack according to the picture, according to the table. This is the first local variable. It is sitting at the lowest point of what we call a call frame, which is a chunk of memory that is relevant to an invocation of a subroutine. So it's at offset 0 because when everything is adjusted, this is where the stack pointer would be pointing to. So it is at an offset of 0 from where the stack pointer is pointing to. Is that okay? All right. And then you have more local variables. So the second variable as a label is defined to be the first local variable plus the size of the first local variable. And then you just keep doing this until you get to the last local variable. Your last local variable as a label is going to be at an offset of the second to the last local variable plus the size of the second to the last local variable. So this is how you basically compute the offset from where the stack pointer points to each and every of your local variables. After the local variables, I define local var size or local variable size. So this is the total number of bytes that we need to allocate for all of the local variables. The way it is computed is simply the last local variable plus the size of the last local variable. So that will give you the total number of bytes that the subroutine, the callee, has to allocate on the stack in order to reserve that space for the local variables. Are we still doing okay so far? Are there any questions about the concept? Yep.
What if we had 3 local variables? So how would that look? So
Well, there's just a bunch of stuff between the first and the last.
Mm-hmm. So they would say, is there a formula for that too? Is it follow suit? Because it says second and the last local variable is equal.
Yeah, you can see the comment of // dot dot dot.
Mm-hmm.
Yeah, that's just basically saying, okay, as many local variables as you have, just follow this pattern.
So the current local variable is equal to the first local variable
The one before.
The one before it.
Plus the size of the one before. Right.
Okay.
Yep. Mm-hmm. Because we're trying to figure out how big of a block of memory do we need to reserve for all of the local variables and where each one is at within that block.
Okay.
So that's why, if a local variable takes up more bytes, well, we have to kind of take that into consideration when we try to compute where the next local variable is going to start.
Okay. Makes sense.
All right, cool. All right, so So local var size is a useful label because we can use it later on to determine how much stack space we need to reserve inside the callee. Return address is located at local var size because remember we are allocating the local variables below where the return address is located, and this picture here once again is going to be useful because initially this is where the stack pointer points to because it was last pushed by the caller. The spaces for the local variables has to be reserved by the callee, not the caller. And then, yeah, go ahead.
So that means the stack pointer is gonna point to, at the end of all of this, it's gonna point to pretty much local var size?
When this is all done,
Yeah.
the stack pointer would point to the first local variable. Yep.
But that's tracked by like local var size, that's why we're tracking local var
That
size.
is correct because that would tell us how many bytes we need to allocate. So local var size is basically how many bytes correspond to this portion of the stack. From the first to the last, what is the total number of bytes do we need to reserve for our local variables?
Just the local variable, not with everything else on top of it.
Just for the local variables. Yeah, the highlighted portion here, they're all our local variables. Since I don't know exactly how many, so I can only say the first, and then the last.
Yeah.
So in between, you can have like, a whole lot,
Right.
or you can have just one single, or you can have none. Okay, so when you have none, then local var size is just going to be 0 because there are no local variables that I need to reserve, bytes for on the stack. Is that okay?
Yeah, and since it's just 0, it's gonna stay at the original return address.
That is correct. That's where the stack pointer will be pointing to after we quote unquote, adjust the stack pointer for local variables
Yeah.
because there are no local variables to begin with.
Gotcha.
Yep.
Putting the first local variable, that's the last thing that you get to, but the stack isn't the highest address is the first thing you,
Say that one more time.
and the stack isn't the highest address,
The stack pointer is always kind of moving around. So we don't know exactly where the stack pointer would be pointing to before the invocation of this particular subroutine, nor does it matter.
Okay.
Because we are just because everything is relative to where the stack pointer points to. So we are basically saying, before this invocation, the stack pointer is pointing to something before or higher than this byte here. And where is it exactly? We don't know, and we don't care. As long as there's enough space for this entire what we call a call frame, we're still good. Because I can find every single one of these items as at a certain fixed offset from where the stack pointer points to. Now, the stack pointer may be moving around, okay? But as long as I know the stack pointer, I can now find every single one of these items at a fixed offset from the stack pointer, from where the stack pointer points to. Is that okay? All right. So when we write the code, hopefully that will also help to kind of make the connections between the concepts. All right, so we have the return address, and then the first argument is at return address +1, because the return address takes up 1 byte in TTP, because the TTP is a 8-bit architecture, so even addresses are only 1 byte wide. And then the second argument is the first argument plus the size of the first argument, and so on. And then the last argument has an offset of the second to the last argument plus the size of the second to the last argument. Just like when we computed how much space is needed by the local variables, this is how we find the offset to the last argument or last parameter in this case, because we are looking at things from the perspective of the callee. All right, are we doing okay or not? Okay, all right. So once we kind of at least have a general idea of the concept, now we can look into the code of how to do this. There's a little bit more after this. This is how we allocate for the local variables. we basically just load the value of the number of bytes that we need to reserve, subtract that much from the stack pointer, and now we're done. Is that okay? Because when the stack is growing, the stack pointer goes lower. At the end of the subroutine, we have to remember to do exactly the opposite, because otherwise the return address would not be at the right place. So we have to remember to add local var size back to the stack pointer, so the stack pointer will go back to point to the return address before we actually return to the column. Are we doing okay or not? Okay, all right. So now we are going to take a look at the C code that we just wrote and then try to translate that into assembly language. There are a few kind of tricky things in this particular program. We'll address the ones that are, in a way not as important, and then we'll address the rest. So we have a no op instruction, JMBI to main. That's kind of the usual template that I write my code now. So we have string length, and then we can automatically put in the return instruction, which is LD, BD, increment D, JMPB. Even though I'm just doing this kind of mechanically, you really should understand what each instruction is doing and how, as a combination or as a sequence of 3 instructions, what they are actually doing. So they are basically popping the return address and then continuing execution at the return address. And then we get into main. Main is going to start with halt, and we also have to remember to initialize the stack pointer. So this is kind of like a generic, skeletal template of programs that we write. So now we got a few questions. The first one is, even main itself has a local variable that I call length in the C code. So how do we allocate for that length? And then how do we access length? Okay. So I'm going to try to make this kind of more universal now. So I'm going to say, let me follow the template that I mentioned earlier in the browser. So this is the format that I want to follow. Okay, we have the first local variable starting at the offset of 0 from where the stack pointer points to. Okay, so length is the only local variable of main, which means it is the first as well as the last. Does that make sense? Okay, so now we say main length as a label is defined to be 0. Now, the reason why I use main underscore as a prefix is because with this assembler, it is really limited. You can only use one single file to describe the entire program. So if you use length again in another subroutine, then the 2 lengths will collide, and the assembler will not let you define the same label twice, which is a problem because there's no quote-unquote local scope. I suppose that's something I should add to the assembler, maybe in the future. But right now, I'm just going to use this as a kludge so that I can avoid the collision of names between subroutines. Is that okay? All right. And since this is the only local variable that we have in main, we can now conclude local var size. So main local var size, okay, because otherwise it's going to take up too many characters. So LVS is local var size. So that's going to be main underscore length plus the width, the number of bytes of length, since it is an unsigned 8-bit integer right here. So this is just a 1 plus. And then we don't have a return address. Okay, main does not have a return address, not in TTP, because main is not really called from anyone else. So there's really no place for me to return to. So we are done with all the label definitions at this point. But label definitions does not actually affect the stack pointer. In other words, as I define your main underscore length, main underscore LVS, the stack pointer is not affecting anything at runtime. Those are not instructions that we execute at runtime. We're simply defining labels so we can refer to numerical values by their symbolic name. So this way I don't have to remember, oh, it's supposed to be 1, this is supposed to be 3, and so on. So this means we still have to allocate the space on the stack for the local variable of main. So now I use the more generic way of doing it, which is LDIA with main underscore LVS, local var size, and then we do a subtraction from the stack pointer. And I would do exactly the opposite at the end of the whole thing, just so that the stack remains balanced. So let me turn on the line numbers so I can refer to those lines. So line 13 and 14 is for the allocation of the one single local variable of main. Lines 16 and 17 is for the deallocation of the local variable in main. So all the code that I need to write has to be between line 14 and line 16 to make use of the local variable. Are we still doing okay so far with this? Yes, no, maybe,
Maybe.
maybe. Okay, which part is not, which part is the maybe part?
So on 12, the LVS,
Mm-hmm.
that's the length or something?
It's the local variable size.
Okay.
So it's basically the total number of bytes for all of the local variables in the entire callee. So in this case, there's only one because according to the C code, length is the only local variable that I need to worry about. But if I have like 20, local variables, then LVS or main LVS is going to be, more than one. So it would help if I make a spreadsheet just to kind of show how the numbers are calculated. But I can do that after this program is written. Question?
No question, I was just looking at the side by side to the
Mhm.
notes.
Yep.
Trying to see if it lines up.
Yeah, you guys can also open up the actual note on your own browser if you have a device. So this way, you can focus on the code on the projector, but at the same time refer to the notes on your own monitor. Shall we proceed? All right. Okay, so let's say we are proceeding. Okay, you guys can, if you can think of a question to ask, do not hesitate to ask at any point. So now, okay, my pointer is at the wrong place. So right now in the C code, we are now ready to implement this function call. So when you look at something like this, the way you think about how to implement it is to think about the ordering of things. Unfortunately, we read from left to right. So we naturally would think, oh, we need to handle length first, and then we have to kind of figure out, how to call the subroutine. But that's not the order of how we do things, okay? Because in an assignment statement, what we need to do is to figure out the value of the right-hand side, and then we take that value to update the left-hand side. So that means reading from left to right is not necessarily the best way to figure out the ordering of how we do things. So even if we were to focus on just the right-hand side, the string length of tag, right? Reading from left to right is also not the best way to do it. Because when we call a subroutine, do we do the JMPI to string length first, or do we do something about the argument first? We do something about the argument first because we have to remember to push the argument, then we push the return address, then we branch to the subroutine that we are calling. So once again, reading from left to right is also not helping. So you kind of have to keep that in mind, okay? It's not reading from left to right that is important. It is trying to figure out what needs to be done first, and then what, and then what. That sequencing is important. So in this case, we have to push the argument first. So now the question is, how are we going to do this, right? Well, as it turns out, a string like this, you are pushing the address of that chunk of characters. Okay, you're not actually pushing the ASCII code of T, the ASCII code of A, the ASCII code of A and then K onto the stack. You're pushing the address at which point TAK as ASCII code can be found. Is that okay? All right. So if I were to translate this into C code, it would be something like this, okay? It's not exactly the same, but it would be something like this. So we have cons char, I'm going to put, I use underscore underscore to mean, something that you're not supposed to see. So this is supposed to be only seen by the compiler itself, but the compiler is going to do something like this. It's going to come up with some gibberish name like that. And then it will say, this is an array, and it's going to contain tag. And over here, the compiler is going to say, that is what I need to refer to, okay? Underscore underscore UFIAU, okay? That's basically what the compiler would do when you specify a literal string. Is the compiler would actually, make an internally known array of those characters, but you won't see it. It will just define it and refer to it, but you're not going to see it. But this is what the compiler does. So in order to translate that code into assembly code, that's kind of what we need to do too. Is that okay? All right. So now the question is, okay, fine, if the program is like that in C code, how do we translate that into assembly? Kind of the same thing, okay? We define the same label, UFIAU, colon, and now we need to use the byte directive to spell out the ASCII code of uppercase T, lowercase a, lowercase k, and then the null terminator after that, okay? So we can look it up, okay? We can look up the ASCII code table. If you're using Linux, there's an easy way to do it because you can just say, oh, not this one. Nope. Okay, I got, okay, X, A, there we go. So you can do a man ASCII, which is the manual page of ASCII. And then we can just look up, what is uppercase T. It is 84, okay? So I just want to direct your attention to here. It is 84, that's T. And I want to make sure I'm looking at the right base. Yep, the second column is decimal. Getting to the wrong place here. Alrighty, that's also the wrong program to look at. Get out of this. This is the right one. So 84 is uppercase T. I know what A is. Lowercase a is 97. And once we know what lowercase a is, we can also count using our fingers to figure out what is lowercase k. So A, B, C, D, E, F, G, H, I, J, K. So that's plus 10 or 11?
11.
Plus 11? Okay, so it would be byte, and I don't even want to trust myself with adding 11 to 97, so I just use the assembler to do the calculation for me. Okay, there we go. And don't forget the null terminator, because without the null terminator, string length would move on and consider the opcode of LDI to be a part of the string, and that would not be good. Okay, so that's why we have to put a null terminator right away at the end of the 3 characters. Okay, so knowing that, what do we need to do now to push underscore underscore UFIAU on the stack? Well, as it turns out, this one is not a local variable. This is a quote unquote global, or at least static, local static variable, which means the label itself is the address. Okay, the label underscore underscore UFIAU, that is the actual address of where I can find the bytes corresponding to tag, the string. Okay, so that means pushing this one, it's easy. Okay, LDIA with the label itself, UFIAU, and then just decrement the stack pointer, STDA, done. And now we can push the return address because we just took care of the argument of the call. So now we can push the return address. So depending on how you want to do it, this is the way we did it before. So LDI dot A with dot 5 plus, and stda. This is pushing the return address. And after we push everything, including the argument and also the return address, it is time to do a JMPI to the subroutine, which is called string length, like so. When we return from string length, the return address itself is going to be popped because according to the agreement, it is the call lead's responsibility to pop the return address. But there would still be one additional item on the stack, that being the argument. So the caller, which is main, is responsible to deallocate the argument. So we have one increment D here to kind of get rid of the argument on the stack. So at this point, register A is going to contain the string length of tech. Okay, and what we need to do now is to finish the assignment operation here, which means I need to figure out where length is as a local variable of main and copy the value of the string length of tech to the local variable length. Is that okay? Does everybody understand what I am about to do? I got the right-hand side already. Okay, the right-hand side is in register A, but now I need to store that to whatever the left-hand side is specifying, which is the local variable length. Is that okay so far? Okay. So this is something that you might recall from the lab on Monday. I'm going to do LDI. I cannot use A anymore, okay, because A is important to me, because A contains the return value of the call to string length. So I have to use register B or C in this case. I'm going to use register B. And this is what I'm putting into register B is the value of the label main underscore length. Because that is the offset, okay? The label main length is the offset from where the stack pointer points to where I can find the local variable length in main. So I'm putting the offset into local variable A first, and then what I do is I add B, D. So this way B becomes the actual address of local variable length on the stack for main. Do you guys remember this instruction or this combination of instruction in Monday's lab? Because in Monday's lab, there was one question that started off with LDIA with some underscore, and then I claimed that when the function is done, it's supposed to return the value of the parameter. This is kind of the same thing. Now, how come this one is a 0 instead of a 1, like the one in the lab on Monday? The one on Monday is an actual subroutine, so there's a return address. But main is not really a function. It doesn't have a return address. So that means the local variables get to, well, in this case, these are local. Length is a local variable. So it really just starts with the offset of 0. So by the time I get to line 35, register B now has the address of length, which means, oh, okay, if we just need to store into that, that would do the trick. So STBA is going to do the trick because at this point, register B has the address of length. I did not write the comment for a reason because I think it would be a good exercise for you guys to just remind me to upload this code. Okay, I can upload it, not a problem. But it would be a good exercise for you guys to comment the code yourselves. So this way, as you write the comment of each line, you're trying to reconnect how those concepts are related. Is that okay? So I verbally describe what each line is doing already. So if you just kind of go through the video and just kind of listen to what I say as I go through this code, you would have the idea of what is really happening, what is the purpose of each line of code, but then you kind of try to write it out as comment in your own words. I think that would be beneficial. So that's main, and this is an awful lot of code already. and I'm not really sure whether this is working or not. So when you're debugging code, if this is your job to write code like this, then I would probably stop right now and go to string length and just specify a awkward and stupid return value. We'll just pick a specific value of 68. Why 68? I have no reason. It just popped up in my mind because I want to see if this code is working. At least I want to see if whether main is working. If main is not working, why would I want to be considered finishing string length? So I'm trying to write the program step by step. Are we still doing okay so far? Okay, so if I were to run this code, what is going to happen? Which location in RAM should be changed and how should it be changed? Or which locations should be changed and how would those locations be changed? All right, so this is where we can use a table, and I'm going to use a spreadsheet for that purpose. I can use a local spreadsheet. Go to Office, Calc. All right. That might be too big. Let me reduce the size of the window first, and then we'll put it into your view, like so. Okay. So what we want to do, what I want to do, is to run this program mentally without even using Logisim, because this way it gives me a baseline of what I should be doing or what I should be seeing when I run this program in Logisim. First thing is I need to label all of these columns, which is location, FF, and so on. So I'm just thinking about how to do this because I don't want to write FF, FE, FD, and so on manually. That's just not a good use of time. So I'm just going to say it's going to be 256 minus the row number of each cell. Okay, so we got 255, and it goes down just like that. But you guys are going to say, yeah, but the simulator reports everything as in hexadecimal. This is not in hexadecimal. Okay, we can fix that. So we can now say dec to hex. If I remember correctly, that's how it's spelled. So now we can kind of do the same thing here. Haha. So now we got the addresses, right? So with all of these addresses, how is that going to help me? What is going to be at location FF? What is the purpose of location FF in this entire program? So you have to, go ahead.
It's where the stack pointer begins.
The stack pointer starts at 0, 0. So what was the first thing that we reserved space for? Let's go back to the code. Okay, so let's go back to the code and find out what was the first thing that we reserved space for. So we have to look back to main. So whenever you look at the reservation of space, we are decreasing the stack pointer. So when you look at this code here, starting with the main label definition over here, what is the first line that would decrease the stack pointer? Sub DA, yep. So line 21, okay, line 21 is the first time that we reserve something. So that means whatever that line is doing, as long as A is not 0, that is corresponding to the answer, that will help me answer what FF is reserved for. So based on, so we know line 21 is of interest to us, but we need to find out what A is, right, to answer the question. So we go back one line. What is line 20 doing? Line 20 is saying, okay, this is how we want to initialize register A, and what is the meaning of main underscore LBS? What is that corresponding to? LBS is the abbreviation of
A local variable
size. Yep. And what is a local variable of main? It only has one. Length. Very, very good. So length is the only local variable. So that means if I go back to the spreadsheet, this location is used by length as a local variable of main. Is that okay? All right. So what else do we put on the stack? So now we go back to the code here. What is the next line that decreases the stack pointer after line 21? Line 24. Line 24 is a very simple decrement D, which means it's decreased by 1. So that means we are looking at location FE at this point. And what did we put into location FE?
Register A, whatever's in register A.
Whatever is in register A, because it's an ST instruction. So how did we initialize register A?
With that weird array. Oh, it's a label.
It's a
And
label.
It's at byte.
And that label is corresponding to
The array.
the array. Yep, the literal string. Okay, that is our literal string. So that means I I can write it like this. Technically, it is correct, but we are not actually putting the 3 characters into location FE. We're putting the address of where we can find the 3 characters in location FE. So in C and C++, when you use double quote, it means you're referring to the address of where we can find the characters. When you use single quote, we are referring to the ASCII code of whatever is enclosed by the single quotes. So we have to keep that in mind because it is really important to differentiate what is double quote and what is single quote in C and C++. Other scripting languages do not do exactly the same thing. So are we good so far? All right. And after that, what is the next time after line 24? What is the next time we decrement the stack pointer? Line 27. And what did we push on the stack that time? The return address. Very good. Okay, so this is the return address to main. Okay. And that was the only thing. I mean, that was the last thing we pushed something on the stack. So I should be able to expect this stuff here to be written into the stack in this particular order before I run the program, okay? But I want to kind of finish the simulation of what this program is supposed to do. So let me go ahead and scroll around a little bit more. So on line 31, we continue execution in string length. String length is not doing much. All it does is to return a value of 68, and then it goes back to the caller. So by the time it gets back to the caller, which is line 33, the return address will be popped, but the address of tag will still be on the stack, and that's why we have line 33 to deallocate the argument. So by the time we get to line 35, FE is not there anymore. The stack pointer will point back to main underscore length, and we load B with the offset, which is 0. We add the offset 0 to register D, which is the stack pointer. The stack pointer is pointing to location FF. 0 plus FF is FF. So by the time we store the A, which is 68 in hexadecimal, into whatever register B is pointing to, it will be storing that to location FF. So that means this location here eventually will be changed to 68 in hexadecimal. That would be 44 in hexadecimal. Because 4 times 16 is 64. 64 plus 4 is 68. So that's how I figure out that decimal 68 is hexadecimal 44. So this is what I am expecting, okay? And then we have a deallocation of all the local variables at the end here, right here. So line 38 and 40 is 39, sorry, line 39 and 40 will deallocate the local variables, so because we don't need those anymore at this point. So the stack pointer should point all the way back to location 0, 0. So I have just run this entire program in my head, predicting what should happen to memory locations, what should happen to registers, the stack pointer, and so on. Now it is time to actually go run it. So this part here, this process is important whenever you write and debug your program. outside of this class or inside, okay? Because when you're writing code for CISP430, you, as the programmer, as the developer, you should still know what the program is supposed to do before you run it. Because only that way you can compare the actual behavior of the code versus what you expect it to do. And this is how you debug your program. You should look at the differences between those two. All right, so now that we got this part done, let's go ahead and give it a try. So we have River Spider, submit, and this is string length dot ttpasm, and I have not saved the file yet. Okay, so now I have just saved the file, and now we can test run the whole thing. It's entirely possible that I might have missed something, so we'll see. There we go. So this is all done. We go back to the assembler. We go to the analysis tab. And if I'm not patient, I would just kind of go to the end of the entire execution and double check that we put 44 into location FF. Okay, that's a good confirmation. The stack pointer went all the way back to 0, 0. That's good too. So I'm fairly confident that this program did what it was supposed to do. Are we doing okay so far with this program at this point? Any questions about any parts of this code before we move on to implement the code in string length? So let me show you the code here. Any questions? No questions so far? Okay. All right. So if there are no questions about this, we are going to continue with the actual implementation of string length here. So we get rid of the useless instruction, and then we get started with this. So we want to define a bunch of labels, okay? Because I want to define my local variable as a label. So in this case, we have string length beginning, and it's going to be 0 because this is the first and last of my local variables. So the label is representing the number of bytes from where the stack pointer points to that I can find this particular local variable. After I allocate for the local variables, the stack pointer should be pointing right at this local variable because it's the only one. Is that okay? All right. And then the next label I need to define is going to be the local variable size, which is going to be the first and also last local variable offset plus the length that it needs. Now, because beginning is a pointer, and every pointer in TTP is just 1 byte wide, so I'm just adding 1 byte to it. This is also where I can find the return address. So if I want to define the return address to have its own label, it's going to be the same as LVS, okay? It's not usually needed. Why would you want to modify the return address inside a subroutine? I can think of a few reasons. You want to hack the program. You want it to return to a point of your choosing instead of the proper place to return to. Yeah, in those cases, you might need to kind of alter the return address. But assuming that's not what we want to do, typically you don't need to know where to find the return address. But we have one more item on the stack that we need to kind of figure out where to find it, and that's my parameter PTR pointer. So that's going to be 1 byte after the return address. So it's going to be string length return address 1 plus. And that's it. That describes everything on the stack that we need for string length. Do we have any questions about the label definitions, the 4 label definitions from line 5 to line 8? They basically describe the local variable, where I can find the local variable, and where I can find the parameter. And also how many bytes I need to allocate for my local variables. Any questions? All right. So assuming that we are good here, we will go ahead and start with the allocation of our local variable and also the deallocation of the local variable. So that usually goes like this. Okay, you basically look at all the string length LVS. We do a subtraction to allocate, and then later on we do an add to deallocate. So the actual code would have to be somewhere between these 2 points. And once again, I have to be careful not to use register A at that point, because at that point, register A has the return value already. So I have to be kind of mindful not to trash register A. All right. So at this point, I'm just doing a straight translation between the C code and the assembly code. So the first line of C code is, okay, go to PTR, grab whatever it is, and copy that to my local variable beginning. All right, let's do that. So this is going to be a pattern that you will see a lot of times. So I'm just going to do a LDI. Register A at this point is free, so I can use register A. It's going to be string length PTR, add AD. Okay, so let me just check to see if you understand the instructions. By the time line 13 is done, by the time I'm done with the adding, what is in register A? And I want you to relate it to the C code. So if you look at the C code and you look at register A after line 13, what do you think register A has at that point?
I think
Well,
it has um, the pointer minus beginning right after that.
no. Well, okay, let's go back and look at the label string length PTR. What is it representing? It's not the return address. I mean, PTR is the name of
The the char pointer.
the char pointer, which is a parameter. Okay? So string length pointer is a label representing the number of bytes from where the stack pointer points to, that where I can find the parameter pointer, PTR. Let me say that one more time, okay? So string length underscore PTR is a label that represents the number of bytes as an offset from where the stack pointer points to where I can find the parameter. Let's go back to the spreadsheet. Okay, so let's take a look at the spreadsheet. And this time I use a new sheet to look at what we can see, well, what we can expect to find when we are in the subroutine of string length. So we have one parameter, which is PTR, that is pushed by the caller. We have the return address, which is also pushed by the caller. And then we have my local variable, which is called beginning, that is allocated by the local variable. I mean, the subroutine being called, the callee. So when this is all done, when I'm done allocating for my local variable, this is where register D is pointing to. Is that okay? Which also means if I want to refer to everything as D plus something, if I want to refer to the address of everything as D plus something, this is D plus 0, this is D plus 1, and this is D plus 2. So the label that I call string length PTR is simply 2. That's basically what it is. So if you go back to this definition and you track down how PTR is defined, length beginning is a 0, LVS is 1 plus 0, which is a 1. String length pointer is string length return address 1 plus, so that would make it 2. In other words, this entire thing, with all of this typing and whatnot, it really is just 2. So we are loading a value of 2 into register A, and then we are adding the stack pointer to A. So that means by this time, when this is all done, register A is D plus 2. which is also where we can find parameter pointer, PTR. Is that okay? Now, this part has nothing to do with the addition that we are talking about today. This part has to do with everything that we talked about last Wednesday and also this Monday, because we are talking about just the parameter, which is not even a local variable. I just used a way to track it using the labels. So are we doing okay or not?
Not totally clear on the subtraction, addition,
The subtraction, you mean the sub
the
BA?
A and add AB.
You mean this one?
Yeah.
This part and this part here? I mean this part here?
No, the 10 and 13.
10 and 13.
Line
Okay,
10.
so they serve entirely different purposes in this case. Okay, so you have to look at line 9 and 10 as one chunk,
Okay.
and then look at line 12 and 13 as one chunk.
Okay.
So they serve different purposes. This chunk here is trying to allocate for the local variables, and then this chunk here is trying to compute the address of where we can find PTR or the pointer as a parameter. Okay, so at the entry point of the subroutine, okay, at the entry point of the subroutine, this is where the stack point is pointing to, which means we have not yet reserved any space for the local variable beginning that I need to use. And that's what the subtraction of that's what the sub instruction is trying to do, is to move the stack pointer here.
Okay.
So it's the allocation of the local variable. So line 9 and 10 together is just doing what I did in the spreadsheet here. It's allocating for the local variable. And then when we are done with the subroutine, lines 15 and 16 is doing the reverse, because when we are done with the entire subroutine, I don't need beginning anymore. So I move the pointer, the stack pointer to back. I move the stack pointer so it goes back to point to the return address. Okay? So assuming that we are done allocating, and this is where the stack point is pointing to, so that means if I can compute d plus 2, I would have the address of PTR. Is that okay? All right. So I will put in a little bit of comment here, but you might want to expand that, when you have time. Register A now has the address of PTR, which is a parameter, but that's not what I want, because on the right-hand side, I don't want the address of pointer. I want pointer itself, so I need to have one dereference like so that A becomes the actual parameter PTR. That's the right-hand side. Now we need to deal with the left-hand side, which is beginning. So now you will start to see the pattern. So at this time, I cannot use register A because register A has something that is important to me. I have to use register B. So string length beginning, add BD this time. And then this time I have store BA, like that. So what is it doing? Well, the pattern is kind of similar to the previous one. Line 16 and 17 together is computing the address of the local variable beginning and put it into register B. And then what do? Well, we just want to store whatever A has to the location that B is pointing to, because register B is the address of beginning, and that's where I need to store the right-hand side. The right-hand side is already in register A at that point. Is that okay? All right. So that means by line 18, I would have been done with the first assignment statement here. And now we have to specify the loop. So I hope you guys still remember how to work with loops, because you need a few labels. So you have the while begin, okay? So technically speaking, you want to prefix all the labels with string length just to make sure there's no collision of the labels. So I'm just going to make it very verbose here. This is the while one loop, in case there are multiple while loops. And this is the begin label. And then we have an end defined here, while one end. And then in between, I can now specify the while loop. So if you remember the template, we want to look for the reason to exit the loop. In other words, we want to check if PTR is pointing to a null character, and if so, we are exiting the loop. So that means I need to go back to PTR and figure out, whether it is pointing to a null character or not. Okay, so this part here is going to look a little bit familiar because it does use some of the code that we had earlier. Okay, so we first have to compute the address of pointer, and then the next thing we need to do is to do a LDAA. So now we actually get pointer itself. But when you look at the condition here, it's not comparing whether pointer as a pointer is null or not. It is comparing whether the character pointed to by pointer is null or not. So that means I have one more dereference to do. So now we have another LDAA, and okay, let me try to do this in a slightly better way. So I'm going to move this one to register B, and this is going to be B and B here. Okay. So there's a reason why I want to preserve the value of register A. I will show you later on why I want to preserve that. So by the time I'm done with line 24, register B contains the character that is pointed to by PTR as a parameter. So this program will give you plenty of work to do over the break, because what you need to do is to comment every single line, but you also want to get a mental picture of what is on the stack, what is each register doing on each line, because that is the way that you make all the connections. Okay, I know it sounds like a lot of work, but the moment you start to understand, how things are organized on the stack, it will get easier and easier because it's going to be the same pattern over and over again. So now that we have asterisk PTR in B. So I'm going to give you some clues. I will drop some clues along the way. So register B now has whatever PTR is pointing to. Well, I just want to see whether it's null or not. So the quickest way to see whether that is null or not, I have to keep pressing space one too many times. So we do an AND BB, which forces the content of B through the ALU, which then affects the sign flag and also the Z flag. So now I can check the Z flag and say, hey, if it is 0, let's get out of here. While one end. There we go. So the code from here all the way to the unconditional branch to the beginning of the loop here, that's the body of the loop, which is just to add 1 to PTR. All right. So it sounds like a lot of work because I have to recompute the address of PTR and then dereference, get it what it is, and then store it back to where it's supposed to go. Well, the good thing is, at this point, I can actually, count on register A still having the address of PTR. I still got it, right? And I also have register B containing the value of PTR because of what, oh, no, I cannot do that, can I? Okay, so do you guys want me to optimize this, or do you want me to kind of go with what we have here? Because I can optimize this a little bit. Let me optimize, okay? Because I want you guys to kind of see what each register has. So register C has whatever PTR is pointing to. So at this point, okay, I want you to answer these questions. What is A? Okay, A equals to what? What is B? And what is C? So try to answer these questions because I think trying to answer these questions is going to be quite beneficial to understand, how the code works. All right, so in the loop here, I'm just going to, I'll write the code, but I'm not going to explain it too much, okay? Because I want you guys to kind of think about what is in register A, B, and C. So here I'm going to do an increment B, ST, A, B, and that would do the auto increment. That's all I'm going to say. Now, whether this works or not, we'll find out soon enough, but I think this is going to work. So when this is all done, by the time we get to while one end, it is time to perform the subtraction. So we have to figure out what is PTR and what is beginning. And I'm going to claim that PTR is in the register already. I don't need to recompute what is in PTR. So I just need to recompute what is in beginning. So we'll do a LDI. So let me see which register has that. Okay, so I can reuse register. I can reuse register A. Okay, or C. Okay, I can reuse register C. So I'll load C with string length beginning, add CD, and then do a LDCC. Now we are ready for the subtraction. So we have a subtraction of BC like that, like so. But since we have to return the value in register A, I have to copy that to register A like that. And now we're done. Okay, so I did not explain a bunch of stuff, okay, because I think that will be your exercise over the weekend, because we are gonna meet on Monday. Yes, I know Thanksgiving is tomorrow, and I know you need one day to get over the food coma, but still, okay, I think this is going to be a good exercise for all of you to do. So I think this code is going to work, but I cannot confirm that until I run it. So let me save the code first, and then I'll go ahead and run it. And the length is supposed to be 3, so I think location FF should be changed to 3. If it works, good. If it doesn't work, even better, because then I can show you how to debug a program written in assembly. All right, so it did not assemble correctly. I made some syntactical mistake, probably misspelling a label or so. So let's go ahead and check out why it is not assembling. So to check out why it's not assembling, you go back to the source tab. Column B will give you the error message. So right here it says while one end is not defined, because everything should be prefixed by the name of the function, and I forgot to do that. So that would be a pretty easy fix. Just find all the labels, make sure that they are all prefixed correctly. So this one it needs to be prefixed. This one is a definition. This one needs to be prefixed. So I caught 2 cases where it needs to be prefixed, and let me see if there are only 2 of those mistakes in the code. Yep, there are only 2 of those, so I think we are good here. So we'll go back and try to run the code again. Nope, still doesn't like it. Okay, first, did I save the file? Nope, I forgot to save the file. You can tell because of the little plus sign here. It tells me that I modified the content, but I did not save the file. All right, fine. We'll try again. All right, so this time it's good. It's running the code. Now it's all done. All right, so here's the moment of truth. We go to the analysis tab, and I'll do the lazy thing and go all the way to the end of the trace. And we want to find out, did I end up storing a 3 at location FF? The answer is yes. Did I balance the stack? Yes, I did it. I did that as well. So the program is correct, okay? It implemented what it is supposed to implement, but I left behind a bunch of unsolved mysteries, okay? Intentionally unsolved mysteries, which sounds like oxymoron. But that's stuff for you guys to do over the weekend. So I think I might have said it already, in this class. This is why I do not like to teach 2 sections of the same class, because I cannot remember what I said in each class. But that's my problem. So what you can do over the weekend is to go over the code, okay? Go over the source code, which is here. I can upload the source code, so that you can have a copy of this, both this and the C code. And what you need to do is to comment on each line of what it is doing. Okay, now if you don't want to write it out, that's fine. Okay, but mentally you have to look at each line and ask, what is this line doing? And I'm not really just talking about, oh, it's adding the value of register D to the value of register C. Okay, that's not what I'm referring to. I'm referring to when this is done, what is register C? How does it relate to an item on the stack? Which item are we talking about? And how does it relate to the C code? Which part of the C code is this a part of? And what is this part doing with that part of the C code? That is the connection that I want you guys to make when you go over this code. But you cannot do this, okay, until you have a clear concept of how things are organized on the stack. So that means the picture that I have here in the module, this picture is going to be helpful because you have to identify when you're in string length, what are the arguments? Okay, what are the parameters in this case? PTR is the only parameter. Um, where's the return address? Okay, it's right below pointer. And do I have any local variables? Yes, I have one single local variable. It has the name of beginning. So now we have one local variable. You got a return address, and you have one parameter. Those three things would be the core frame of string length. And then you have to relate to the C code. I mean the assembly code. Sorry. So you have to relate to the assembly code of what are these labels doing? From line 5 to line 8, what are they doing? Each label is defining an offset from where the stack pointer points to one particular item. How is that calculation done, and why is it done this way? And then you have to ask, what are lines 9 and 10 doing? And they are matched by lines 43 and 44. What are those lines doing? How do they relate to the picture that we have here? Is that okay? So on Monday, when we meet again, you can ask questions about this. Okay, if you cannot make some of the connections, you can ask me and ask, okay, I don't see how this line of assembly code is doing something useful, or I don't see what it is connected to. Why do we have this line of code? So that's one thing you can do, is to comment the source code, but the assembler also gives you the runtime trace, which is what we are looking at, using the analysis tab. So you can comment this one as well. In other words, you can just kind of print this out on a piece of paper. Let me see how it prints out on on an actual piece of paper, because I want to make sure that all the columns fit and still give you some space. Yeah, so I think it gives you enough space to kind of write out whatever you want to kind of annotate it with. So I would do that because this one it's only like what 3 pages long, which is not really long. Okay, so I would do that. I would definitely look at the actual trace as well. Now the trace is useful because it actually shows you what is happening to the stack pointer. It also shows you exactly what is happening with the content on the stack. When did we push something on the stack? What exactly did we just push? What is this, 2, 0 here? What is that? How does it relate to the C code? Well, those are the questions that I want you guys to be able to answer over the weekend. So today we do have a lab. The lab also has a component that's going to be due next Wednesday, so you got a week to work on that one. But I would do this part first, okay? Because once you understand how arguments work, how local variables work, how pointers work, then you can work on the assignment that is due next Wednesday. So I would do this part first, is to really thoroughly understand this particular program, because that will give you ideas of how to um, get the assignment done. All right. So I also want to emphasize, because it would appear that people do not seem to know, is I do have office hours on Mondays and Wednesdays right before this class. I intentionally make that office hour so that it's convenient, so that you guys can just show up a little bit early, go to my office, ask any questions, have me to take a look at your program and stuff like that. Okay, because this entire semester I have yet to have anyone to show up. Maybe what I need is just candies or something in my office. Skittles. But it won't stay very long in my office because I'll be the one finishing it. Skittles. All right. So that's it for the lecture, and I'm going to release the lab. The lab should be released already. You just don't know the passcode. All right. So today's lab has a very deceptively simple name because the name is just function calls. And I think the passcode is swap. SWAP. That's the passcode. So you should be able to get into the um, lab for today. There are two components, by the way. One is due today. Those are the multiple choice questions and stuff like that. And then the actual program is due in a week. But I would not procrastinate if I were you, because this program is not easy to do. It's a good test of whether you understand the concepts of this class or not. So I would first try to understand the sample program that I did today. I will send a copy to you, all of you, and then once you have done that, I would start on the sample program. I mean the actual program due next Wednesday. All right. So do we have any more questions before I stop the recorder? No questions. All right. So if there are no questions, I'm going to stop the recorder and get things uploaded.